and welcome to my talk. I'm Ken, and here I'm giving a talk about AFL's blind spot or small limitation about AFL and how we can use it to resist AFL fuzzing against arbitrary binaries. First, a brief introduction about myself. I'm a professor from the University of Georgia. In the past, I have been doing a bunch of CTF work. I helped organize a few CTF teams, the relatively well-known one, including SecDocs, and I'm the founding mentor for the team Blue Lotus. I also helped found a team called Dissect. I'm also a player of there. Dissect was one of the finalists in the 2016 DARPA Cyber Grand Challenge. Recently, I'm on sabbatical leave. Currently, I am the team lead for the 360 cyber immunity. So come back to the talk. When I explain to other people about AFL's limitation and we can use it to resist AFL fuzzing, very often they ask me a question. The first question they ask is, why do you want to resist AFL fuzzing? So I have to, there's many answers to this, but I'm going to use one of them related to my own experience. I just mentioned to you that I am a college professor. I teach cybersecurity class. So when I teach software security class, I often assign like a buggy program to my student. I ask them to try to reverse engineer it, look at the binary. And certainly during that time, usually the student take a while to do it, so I can rest. Or maybe during that time I can write a submission to Black Hat. Here's the example I use in class. Like this is a simple function. It takes the input, and if you have a special input string like magic, and the program will crash. Otherwise, it will ask the student to try a different input again. Now, for a binary like this, if I compile it, I strip the symbol, I give the binary to my student, it actually takes them a while to finish. For people here in the audience, I expect you probably finish in 5 minutes, but my student usually take like 45 minutes, whole class time, or maybe hours. Okay, so I call those the old peaceful class time. Now, of course, you know what happened like recently when I gave this challenge to my student, they just simply run AFL. And AFL, like for that particular example, it takes like 2 or 3 minutes to find all the passes, and certainly one of them lead to the crash. So that's what I call the peace disrupted. My peaceful time, that I can rest no longer there, okay? So that's one of the reasons I tell you why I'm doing this. I prepare this software tool like I call it DFL or DFL, and what it does is it try to change the binary so that AFL, when it fuzz it takes much longer, right? So then I can force the student to look at the binary rather than just run the AFL. I would rather them to open the binary, or maybe even just IDA disassembly. I want them to do that rather than just run AFL. Certainly, there are other reasons we do this. One of the reasons I also mentioned to others is that we want to really find challenging program for AFL, try to see its limitation, and we want to improve. We're trying to get better fuzzers. Now, certainly there are evil minds that really just want to hide bugs. That's also another possibility. You can imagine that. So for the rest of the talk, I need to first explain the blind spot of AFL, or AFL's small limitation. So let's give a really quick overview about how AFL fuzzing works. So I'm using this 5 steps to summarize the high-level process of AFL fuzzing. So first, AFL has to start with some seed input. Okay. Once you have seed input, the next step AFL does is it takes seed input, it modifies some of the bytes, and you can call this mutation, and AFL take a seed and then mutate to a new mutant or a mutated input. And after that, AFL will run this target program with this new input and track the code coverage. The detailed code coverage I will talk about in the next few slides. What matters here at the high level is that if AFL run this new input, and if AFL believes the coverage increased, then AFL will take this new mutated input and put it into the place, AFL queue, which is the place that AFL keep all the seed there. So you basically have a new seed. If there's no coverage increase, then AFL will discard this. And then the whole process will start from the step 2. Okay, so that's the high-level process. Now the important part is that AFL uses a really compact, small data structure, the shared mem part, like D464K, to keep track of all the edge coverage. And this is one of the sort of the main contribution like AFL used to get it run fast and efficient. And because of this, AFL actually is very successful. I don't need to really go into the detail about how successful they are, but you can go to the website of AFL and you can find lots of bugs found by AFL, by lots of other people. And one thing I can definitely add on to say is that in the 2016 DARPA Cyber Grand Challenge, the seven finalists, all of them almost use AFL as part of their solution. Okay, so that's how successful they are. But let's look at the detail, the coverage information, how they track. I mentioned that AFL uses small compact bitmap to track the coverage. The way AFL does this is AFL uses code instrumentation. If you have source code, then AFL, if you compile code with AFL GCC, what AFL does is to put a piece of code at each of the code block. What this code does in general, you can consider the following. It assigns a random number to each of the code block. And every time your code execution go from one block to the other, you just basically take this 2 codes random number, you do XOR, and that you use that as the index to index your the small bitmap, then you mark there. So that's how you track the code coverage when you have source code. Now for this talk, we're interested in the case that you only have binary. So it's not that easy to modify the code to just add this instrumentation. So what AFL does, there are multiple ways, but the dominant way is using AFL QEMU, and it modifies QEMU. So every time when QEMU hits a new code block, instead of using a random number, because you cannot easily modify the code, instead of using a random number, you're actually using the code address, the current code block address as the seed to do this hash. Okay, so I show the code there. This is the simple hash they use. Now, to illustrate this example in a little detail, I'm going to use this control flow graph from the program called readelf, and I actually show a partial one in the middle of this picture. Now let's assume we have a test case called test case 1, and we're running with AFL, and suppose the execution for this test case 1 goes through this yellow line, and in this partial CFG we touch like 3 basic blocks. Okay, and AFL captures the edge coverage, so between each pair of the block, AFL, using the early hash algorithm I mentioned, it generates a hash and then indexes bitmap. If you, in this particular case, in this small picture, we have another block being covered, so the second edge also, we do a hash, we mark the corresponding bits in the bitmap. Now, assuming initially you have empty bitmap, now you run this, you show that 2 places been marked, then you know that this test case have new coverage. As a result, you want to add this test case 1 to your AFL queue as your seed for future mutation. Okay, so you put this into queue. Now let's say you get another test case called test case N. Okay, now you run this, and suppose on the picture we know it goes through a different path. And if you look at the first 2 blocks, if we do the hash and it go to the bitmap, if it hits a place that has previously not been marked, then you find some new coverage again. Conceptually, you know this is a test case that find a new path, so AFL consider this is something worse to keep mutating, so we'll save this to the queue too. Okay, so test case N also put into the queue. Now let's look at the third case. This case suppose we have a test case called test case X, and we have an execution that goes through the blue line, okay? And this is, on this picture, I marked all the blocks that have been covered in yellow, and the blue line actually touched 2 blocks that are not being used by the previous test cases. But what if the hash of these 2 addresses that end up index bits that are already been marked by previous, because of hash conflict? As a result, in this case, this test case X even is cover new passes it's not going to be taken. So this is what we call the AFL's blind spot. Now, the developer of AFL knows that the bitmap hash conflict, there's a problem. So they have recommendation to say, if you run AFL over a program, you should watch for this report called map density info on the screen. And if it's more than, let's say, 20%, you probably should think about something else. Either make a larger bitmap or maybe only fuzz a part of the program. Okay. Now, what we find is that it turns out that even for small program like readelf, we find that the hash conflict actually happen much more often. So what happened is during our early work on the Cyber Grand Challenge and also the later work, we try to combine like symbolic execution engine with AFL. We try to use other methods to help AFL to find new paths. And it turns out that we have the result here, like we use symbolic execution engine to find a path showing the blue line, and all the address and the block are copied from the real code. The blue line is our symbolic execution path found by our engine. And we feed this to AFL. We tell AFL says, this is a path that you haven't found. This is interesting. You should keep notating it. Well, AFL refused to take it in that case because AFL has already covered the two paths on the yellow, indicated by the yellow line. Even there are different paths, but because of hash conflict, AFL will just refuse to take it. So what I want to mention here, I'll emphasize here is that the hash conflict, or the AFL's blind spot, even people know that you should not, you should try to look at the bitmap density and try to maybe change the bitmap size. There are other situations, like when you combine symbolic execution with AFL, you also have to watch this. Otherwise, you might waste your time. You generate test case for AFL in another way, but AFL won't take it. Okay. Now, there's maybe a simple solution. You could say, okay, if we know AFL has this hash conflict, let's just use a larger bitmap, right? So we had a work related to this, talking about the consequence of a larger bitmap. This is published in early this year in the IEEE Symposium of Privacy, Security and Privacy. And so we have two findings there. First, even you use a large bitmap, depend on the type of a hash conflict. There are some hash conflict you can remove it by using a larger bitmap because it's really not the size of the bitmap size. But there are other hash conflict you just cannot get rid of it. So larger bitmap size does not guarantee you don't have hash conflict. Second, there's a penalty of using large bitmap. There's a reason why the developer of AFL choose default 64K, because they really want to have the shared memory, the frequently used piece of data in the CPU cache. When you use a larger bitmap, you end up having less chance to have in the cache, then your execution speed slow down. So the picture I show here on the horizontal direction is the bitmap size increasing from 64K to 32 meg. On the vertical direction shows the slowdown ratio. And you can see that, by the way, for each of the line there, it means like for a particular test program we use to show the slowdown. And you can see in general, the general trend is slow down a lot if you use large bitmap size. And the program here we use, there's really a wide range of program, including like TCP dump, clam AV, and a bunch of others. Okay, so that's the part I want to mention to you to say, okay, AFL has this small limitation. You need to be careful about it. Now let's look at how we can resist AFL fuzzing, using this. So first, let's put this aside. Let's say simply we want to resist AFL fuzzing, okay? Now, if you have source code, or if you are the author of the program, you actually can do lots of things. Like, for example, I put a few examples here. Like, one case you can do is if you add a complex constraint, like if you have like input multiply input equal quite large number, that it's really hard for AFL to find it. You can also like introduce like long sleep time for known invalid input. Because AFL's efficiency really depend on how fast they can run through this. And if you write the code, you can try to introduce non-determinate event, or maybe even relocate the code so the hash the edge tracking is not accurate. But what we're going to do here is, in this talk, we're going to try to use hash conflict to try to resist fuzzing, okay? So the general idea is like, we want to insert a bunch of code to the binary so that it create hash conflict with the target path that potentially lead to a crash. So that's the general idea. Now, in order to do this, we need to answer 3 questions. So first, which edge you want to target to generate the hash conflict? Second question, if you have the target for particular edge, how are you going to generate a piece of code that exactly have the exactly hash? The last question is like, how are you going to put this piece of code there? I'm going to answer this in the next few minutes. So the first question, which edge we should target? One naive solution is like, let's just generate a bunch of code, like pollute the binary so that there's all the bits are filled. Okay, you can do that by generating lots of code and to have lots of code block jump back and forth, and you can do that. But the trouble is that first you get the target binary much bigger, and second the code runs very slow. Our goal is like we still want to preserve the original program's function, and we don't want to do this. So our goal is eventually our current implementation is we just want to target a particular a bunch of edge that lead toward the seed that eventually mutate to the crush. So here's what we did. So if you gave me a binary, we will first run AFL to try to find a crush over a certain type, because I don't know where the crush is or where the bug is. Suppose we find one, then we will find which seed that lead to there. So I will explain how to do this in the next slides. So we call this seed our targeted seed. Then we compare the initial seed, their code coverage, and the targeted seed, their coverage, and the difference. And the edge difference are the one we're going to try to pollute or try to cause hash conflict. So give you an example. If you run AFL, like if you have a crush, the file name actually tells you which seed actually help you generate that crush. In this example, the file name tells you this crush actually come from the source 179 and 48. So it's actually have 2 parents. And from those 2 parents, for each of the parents, we can just look at their code, the control flow coverage, and try to compare the difference. So we write a tool, like if you gave a certain seed and you have the initial seed, it will tell you which edge you should target. So that's the list. So that answers the first question. The second question, let's say, suppose we have a target, okay? Like it go from code block X, both code block A to block B. So we have these 2 address, we know hash. Now, how do you generate a piece of code that have the exact same hash? Now, we assume we have a fixed starting address. So we want to use a jump. So initially, we just simply say, let's do a jump. Like we have an initial address, let's find a target. If we jump to the right target, if the target address hash with the same hash outcome with the given one, then we're good. And it turns out, if you only do a jump command, like QEMU, don't consider those are like two new block. So you have to fake a little bit more. So we don't want to add too much code, so we end up we do a dummy compare, then we do a jump. Then we end up able to do this. Now, when you calculate the target, it's actually not that hard. It turns out you can have multiple answers. And also, suppose you have a previous location, you just do this compare jump and you choose the target. You don't, in the middle, we put knobs in it, and you don't have to continue jump down. You can actually jump back and forth. So you end up having a piece of code that you have a nested jump in the middle. Okay, so that's how we created the hash conflict. Now, once you have that, and then the next thing you need to do is you need to insert this piece of code to the target program to generate a new ALF binary. So what we did is we modified the code, the text section, we expanded to put our code at the end. Then we modify the program header to make sure it starts from our code first, because we want to pollute the hash first. Then we jump back to the original code. Now, there are lots of additional work we have to do, because once we enlarge the text segment, we actually we put it at the end because we don't want to mess up the initial code location, because those are the hash we calculate before. But once we make the text section large, Then there are other sections behind it have to change their location, and end up if your text section use any of those, you have to modify the address. So there's lots of labor work there. I just skip the detail, okay? But the general idea is we just enlarge this text section. So let's look at a few examples. First, again, the old example I use in a class, right? This is the path that had the 7 paths, and one of them lead to the crash. And this is the old picture that, if you use AFL, you find it immediately. Now, here's the picture that we show that if we do a little bit of work, then you can see like AFL spend like 20 minutes still on that 6 paths. Right? If you pollute more, then you can see that AFL failed to find the other paths and then like spend like 8 days there. But those are like my program. It's not interesting, right? So you want to see how this effort apply to other binaries. So the first thing we tried is we find TCP dump. There's an old bug, like this is in 2015, right? We know this bug, so we find an input that is close to this, right? And then if we feed that seed input to AFL, AFL like less than 5 minutes find the crash and report the bug. Now apply our tool to this. Then you can see like we generate new binary. I don't show you the result of running this new TCP dump. It's still functioning as a normal TCP dump, but I already ran like 2 weeks with AFL on the same machine that find the bug in 5 minutes with the same seed, and 2 weeks AFL still hasn't found it. Okay. I try other binary because the previous one is like sort of an old bug, and recently we found a new CVE in object copy. So we take that for easy seed input that close to the crash. We give it like 1 minute AFL find the bug. And then in our case, if we modify the binary with our tool, in this case like we run 9 hours and it hasn't found the bug. Okay, so that's a quick summary demo in terms of showing like what we can do so far. But then originally I thought like I find a way to really say, okay, this is maybe a tool or a method to hide bugs. But then I look at this in a little bit more detail. I feel like this is still our method still lots of trouble. At least in the current implementation, first our injected code is really easy to identify. Like for someone, like if they see our binary, they know it can modify the entry point of the program. They can find our code. They can do another round of modification. They can just remove our code. Then they can fuzz again. So, and worse than that, if you think about using this way as to hide a bug, well, our tool certainly kind of gave the hint to whoever want to find the bug. So now, like instead of they do fuzz, they can just follow my jump. That maybe they find the edges to the bug. So that's why the current implementation is more like illustrating the point, but it's not ready to be used as a defense a method, general method to resist AFL. And also there are other methods to do instrumentation and to handle the code coverage collection, information collection, like using Intel PT or Dynamo Real. So my talk doesn't deal with that. And the third point is that even we are successfully to create all the hash conflict, we don't guarantee we remove the chance of AFL find it, because AFL does all this, all kinds of mutation. There are random case that it could be just like even I hide all the edges, but from the initial seed, AFL might just randomly, very luckily, they just might still be able to create the crash, right? So that's some of the limitation with our current solution. But when we look at this, we actually also find lots of other ways to resist AFL fuzzing. So I'm going to just mention a few here. So 2 of the solutions here. When we look at AFL QEMU, it turns out that AFL QEMU only tracks the first text segment. If you look at the patch of AFL QEMU. So a simple solution to avoid AFL to find your code is like you just add another text segment, move all the meaningful code there, and AFL won't be able to even see it. Okay, so that's one solution. The other solution is like if you inject like fake termination signal, like your code say normally has a regular exit point, and you can simply do that by say put a abort there, then AFL will have lots of false positive. Okay, so that's pretty much all I have for you to quickly summarize what I have. I showed you that AFL has a small limitation. That it's really its hash conflict. It's caused by its efficient data structure because it's really want to run fast. And we show you a tool that we can actually write binary to create this hash conflict. So that's all I have for today. And I don't know whether I have a question. I have time for question and answer. If you any questions?
Resistant to UPX, basically to any packers of the binaries.
I assume like you are saying like if there's already a packer, right? You pack it, and I didn't evaluate like in fact, AFL might actually have hard time to deal with UPX packed binary. I don't know, but I think these two efforts can be complementary. I didn't try it, so I don't know the exact answer.
Thank you.
Yeah, thanks.
Hi. Hi. Another question. So this is Mingwei from Intel Labs. So very interesting talk. And so you mentioned about the issue about AFL. So I'm wondering if this could be solved by AFL easily using multiple bitmaps with multiple hash functions.
Right. So definitely you can either modify the hash function, you can use multiple bitmap, but remember why the developer of AFL uses really simple method, because AFL wants really use a very low overhead approach to make sure it runs fast. So every time you add additional effort, like maybe multiple bitmap, larger bitmap, multiple hash function, better hash function, you actually slow it down. So there's the penalty. So if you want to do the trade-off, yes, you can reduce this hash conflict to a certain extent, but you have the penalty. In fact, our paper in the IEEE SMP actually proposed just a modification on the hash algorithm, try to reduce as much, try to really minimize the hash conflict impact. So you can do that, yes.
Thanks.
Yeah, you mentioned the path-sensitive fuzzing paper, I believe you worked on as well. So did you try to run the resisting binaries against this new fuzzer, and what were the results?
Right,
Thanks.
we haven't ran it, but for this particular tool, like DFL, we didn't. But when we evaluate the hash conflict impact in the IEEE SMP paper, and you can find this is called a path-sensitive fuzzing. And we actually tried other fuzzer like libfuzz, homefuzz. We tried a bunch of other ones, and almost all of them have potential this hash conflict problem because they all want to use a compact data structure to record it. So that trade-off is always there.
So when you say you developed a new fuzzer in the path-sensitive fuzzing paper, right? Do you think that resolves the issue?
No, so the work we did there is actually rely on some assumption. It requires you to know the control flow graph, or at least know a rough control flow graph. So then you can avoid if you know initially, if you already know what are the edges, you can make sure when you calculate hash, you can just remove the hash conflict there. But we all know that having a accurate, complete control flow graph, that's itself is an invalid assumption, at least for large, meaningful program.
Thanks.
Thank you. Any other questions? Or if not, thank you.